So you just saw me press a big textbook against the wall, and it was obvious I was only pushing sideways. I held it there with a meter stick. Let's draw the free body diagram, and let's just, so that we have kind of a reference, let's see, the wall was on your right, so let's put the wall right there. There's the book. What are the forces acting on it? Get the obvious one. Gravity. I totally agree. Was the book accelerating down? Was it accelerating up? So I know there has to be an arrow pointing up, bigger, smaller, or the same size as mg. Got to be the same. What force is that? Got to be honest. I'm not sure yet. I'm going to hold off. What else? Well, I was applying a force this way against the wall. Was it sinking into the wall like quicksand? Was it flying off of the wall like Superman? So there has to be a force the same size, eyeball it, in the opposite. What force is that? The wall. I agree and I disagree. I think we can generalize that even a bit more. It's the force that was preventing me from sinking into a surface. What force is that? You know what? That's a normal force. Does that give you any kind of a hint as to what the up arrow probably is? The up arrow is friction. I'm doing the same thing when I'm squeezing my fingers together. I'm applying a force in. I'm getting a normal force out. Friction is pointing up. In fact, as I relax my fingers, you can't see Diego, but I'm relaxing my fingers. I can actually feel it's just about ready to slip. Because by relaxing my fingers, which force was I making smaller? F applied. Which force did that make smaller? The normal force. Oh, and by the way, friction is what times what? I could then make friction smaller and smaller as well. That's just kind of, to me, a neat, interesting, common everyday, anytime you're carrying something from above like this by squeezing it, you're doing that free body diagram there. You take it for granted, but think about it. Using a sideways force, Sarah Ashley, to resist a vertical gravity pull down. Kind of cool. That's not today's lesson. That's just, we've reached the point where we can walk through some fairly complicated free body diagrams. Here's today's lesson. Many body problems. In these problems, we have several objects connected by strings. And we're going to add a restriction. So I have here an example. Here's two masses connected by a string. If the mass in my right hand on your left is accelerating sideways at 2 meters per second squared, what's the hanging mass accelerating up at? First thing we're going to say is, you know what? The acceleration of two objects attached by a rope will be the same magnitude. Different direction, same magnitude. So what we're not going to do, look up, we're not going to let you do this. Those of you at YouTube can't see what I'm doing. I'm yanking on the rope. This right here actually has a name in physics. It is actually called a jerk. And the physics of jerk is very difficult. You really need calculus. It's also really, really tough to study on its own. We haven't come up with very many experiments that study jerk that also don't have acceleration in them. It's a tricky one to isolate and study on its own. So, for any question where you see a mass attached to another mass with a string, it'll be a smooth acceleration, and I'm telling you, they're accelerating at the same rate. Now, why does that help? The easy approach is to realize that we can treat this system as a single object because they're all accelerating at the same rate. Example 1, I like example 1. Actually, you know what? Example 1's a little too easy because there's no friction. Once I get to one that has friction, that one I like, that one I like. Riley, what's example 1 part A wanting me to find?
Acceleration.
And B is asking me to find? Okay. Here's our strategy. I'm going to find the acceleration of everything by writing an equation for everything. Then B, I'm going to find an individual mass by looking, or individual force by looking at an individual mass. Find an equation, the acceleration of everything by writing an equation for everything. Find an individual force by looking at an individual mass. Riley, any thoughts on what might this be a good job for? Yep. So I'm going to free body diagram. What are the forces on the 3 kilogram mass? Get the obvious one. Is there more than one mass in this question? Say yes. So instead of just mg, I'm going to call this m1g. Josh, are we sinking into the ground like quicksand? Are we flying into like Superman? So what else? Is there more than one mass in this question? I'm going to call it normal force number 1 to go with mass number 1. And that will be our high-tech labeling approach. Shko, which way is the 3 kilogram mass accelerating? Right. Which way must there be an unbalanced force?
Right.
Wow. Let's try that again. Which way is this accelerating? To the right. So which way must there be an unbalanced force? Right. Same answer. Right. Right. Your word is right. Which way is this accelerating? To the right. Which way must there be an unbalanced force? Right. What force is that? Not the 20. The 20 is not touching the 3. 20 is touching the 2. What's touching the 3? The rope. What do we call the force from a rope? You're feeling some right now. Good. Tension. Those are the 3 forces on mass 1. Oh, Ruby, if there was friction, I would have one more force pointing that way. I'd call it friction force number 1 to go with mass number 1 and normal force number 1. Cool. Alex, what are the forces acting on the 2 kilogram mass? Get the obvious one. Is there more than one mass? I'm going to call this M2G. Are we sinking into the ground like quicksand? Are we flying through like Superman? So there's going to be a normal force. Good. What else? What's that 20? What name did we give to a mystery force coming from off the page? We'll call it F applied. So, Alex, I'm going to go put an arrow there. I'll put F app equals 20. I'm missing one more force. Can anybody see it? There is going to be a force to the left. What? Yes. This right here, Casey, is a consequence of Newton's third. Forces come in pairs. Oh, the rope tugs on the 2 kilogram mass. The 2 kilogram mass tugs back on the rope on the 3 kilogram. They're tugging on each other. Okay? There's our free body diagram. Now what we're going to do is we're going to write an equation, but our equation is going to be for all the forces along the rope. Which way do you think this is accelerating? Well, we're on ice because it's frictionless. So which way is it accelerating? To the? Which way is the winning direction? To the? So anything that's pointing to the right, I'm going to call winner. I'll put a plus sign in front of it. Anything that's pointing to the left, loser. It's going to have a minus sign in front of it. And I'm going to walk along the rope. Here we go. Winner. F applied. D. What about this tension here? Loser. What about this tension here? Am I done along the rope? Now you'll notice M1G, M2G aren't showing up. They're not along the rope. Am I done? All the forces along the rope? Not quite. Here's the slight tweak we need to make. Do I have forces from more than one mass over here on the left-hand side? Then I have to have more than one mass on the right-hand side. Look up. Don't write this down. Everybody look up. Keep looking up. Technically, it's this. M1 plus M2 times A. But I'm lazy. I'm going to, instead of writing M1 plus M2, I'm just going to say M all A. Write that down. There's our tweak. In fact, you know what? That's what the equation was all along, because when it was one mass, we were technically still doing M all A. When it's 2 masses, 3 masses, M all A. It's always been that. That's really the generic winner minus loser equation, equals M all A. Everybody put your pencil down. Let's Stretch. Oh, man. I find these questions so relaxing. Diego, do you know why I find these questions so relaxing? Because whenever I do them, I lose tension. Oh, it's good. That's not my best worst joke. It gets worse. But I will do a little stretch every time I do these questions because you lose a little tension. Diego, what am I trying to find in part A?
Acceleration.
How would I get the A by itself? Divide by M all. Yeah. In fact, you know what? I'll bet you, Diego, this is so easy that even you can do this in your head. Let's see. Oh, but look up. For my work, if you just did that, showing your work, I'm good with that. You don't need to rewrite the whole equation. Let's plug in our numbers. Diego, what's F applied as a number exactly? Go look at the picture. Yep, loud and proud. Yep. Divided by, remember M all is add them together. What's M1 as a number exactly? What's M1 as a number exactly from the picture? Plus, what's M2 as a number exactly? In your head, without a calculator, what's 3 plus 2? What's 20 divided by 5? Do you get a little nerdy adrenaline rush when you do the math? See, that's what I feel every time I do one of these in my head. I don't get to do math in my head. Okay. You know what? Let's look impressive. Let's go to 2 sig figs just to show off. Units, it's an acceleration. Meters per second squared. Good. Really, that's the whole lesson. I could almost quit and give you the homework, but we'll do some more practice. But Lily, our tweak is going to be, give me more than one mass? Fine. I'll write an equation for the acceleration of everything, and it's going to be winner minus loser equals M all, M everything, times A. Aryan, what did B want me to find? Why can't I use this equation to find tension? What? The tensions cancel. One could almost say that in this equation, there's a deficit of tensions. Do you know why I can't use this equation? Because I have a tension deficit disorder. Oh, yeah! That is such a bad joke. I have a deficit of tensions. The tensions canceled. I'm missing tension. And so I can't use this. Oh, come on. That's gold. Nothing? Fine. That was the best worst joke you're going to get from me in a while.
Emote a little bit.
So you know what, Sarah? Here's what we're going to say. If you want me to find an individual force, like tension, I'm going to use an individual mass. Let's look at the 3 kilogram mass. Let's quickly redo the free body diagram. We had mg down, m1g down, normal force number 1, tension. Okay. Sarah Ashley, which way is the 3 kilogram mass accelerating? To the... Who's winning? Same answer. More specific now here. Who's winning? What's the only force pointing to the right? Tension. Here's my equation for the 3 kilogram mass. Who's losing? It's a trick question. No one. What does winner minus loser always equal? Which mass specifically are we looking at this time? M1A. Do you see how we're just tweaking our winner minus loser equation? What's M1 exactly as a number? What was A? We just found it. In your head without a calculator, how many newtons of tension is there in the rope? Yes. Lily, you know what would be really cool? It would be really cool if to find tension in the rope, it didn't matter which mass I picked. I would get the same answer both ways. And then I could just pick the easiest mass instead of having to use a specific method. Let's retry this and let's look at the 2 kilogram mass. Lily, I seem to recall for the 2 kilogram mass we had M2G, normal force 2, F applied, and tension. Right. Which way is the 2 kilogram mass accelerating? To the, who's winning? More specific in this free body diagram here. Yes. Who's losing? What's that going to equal? M2A. Because now I'm drawing a diagram only for mass 2. I'll get F applied minus tension equals M2A. I'd like to find tension. Lily, what's right in front of the T that I don't like? Swap your dance to get rid of the negative. What was that? I'm going to plus that there, minus that there. I'll get F applied minus M2A. And then, Lily, instead of writing equals T, can I put the T equals on this side? Because that's where we're used to seeing the thing bites. How big was F applied as a number exactly, Lily? Minus, what was the mass? 2. What was the acceleration? 4. It would be really neat if that also worked out to 12, does it? It does? Oh, well, that's convenient. If you give me a multi-body problem, a many-mass problem, no sweat. If they're attached by ropes, they're all accelerating at the same rate. Winner minus loser equals M all A. Oh, and then you want me to find some individual forces? Fine, I'll write equations for individual masses. Which mass? Whatever makes my life the easiest. We can also do this if we have a mass hanging over a cliff. So if we have a hanging mass and no outside forces, well, which way is this going to accelerate? Right and down or left and up? It's got to, if this is a cart with no batteries, it's just sitting there on wheels, it's got to go right and down because gravity's going to be pulling down. Okay. Cool. We can do this. We can do this. We can do this. Jada, what does example 3 want me to find for part A? And for part B? Any thoughts on what this might be a good job for? Good. What are the forces acting on the 6? Get the obvious one. Is there more than one mass? I'll call it M1G. What else? We'll go systematic. Is it sinking into the ground like quicksand? Is it flying like soup? Is it sitting on its normal force? Bigger, smaller, or the same size as empty? Same side. No extra vertical. Same size. No extra vertical forces yet. Okay. Good. I'm going to call it normal force number 1 to go with mass number. What else? Rope. See it? What do we call the force from a rope? Is there friction? I think the wheels are meant to indicate ignore friction. But if there was a mu, I would have just one more force pointing that way. It makes the question a little longer. I can't even really say it makes it tougher. Ooh, what are the forces on the 2.5 kilogram mass? Get the obvious one. Good. Ooh, is it sitting on a surface? So is there a normal force? No, because the normal force is the force from a surface pushing back on you when you push down on it. So is there a normal force? This is why I say don't get normal force loopy. What is there? Rope. Good. Now what? We're going to write an equation along the rope. By the way, is M1G along the rope? It's not going to show up in my equation. What is going to show up? Well, which way do we think this is accelerating? Right and down. Who's winning? What's starting this whole thing? Right there. So anything that ends up pointing down once it gets over here will be winner plus. Anything that ends up pointing up when it gets over here will be loser minus. You got? Okay, Jada, what's my equation? Who's winning? More specific, which one? Because there's several in this question. M2G. Walk along the rope. This tension, winner or loser? Loser minus. This tension, when I follow it, when it gets to here, I think it ends up pointing down, which we've decided is winner plus. Have we reached the end of the rope? Yep. What about M1? It's not along the rope. Going to ignore it for now. If it needs to show up, it'll show up, but not right now. When there's more than one mass, what does winner minus loser always equal? M all A. That's our tweak. Jada, put your pets down. Join me. Come on. Oh, why am I stretching? Why do I find these questions so relaxing? Oh, you always lose a little tension when you're working on these. This is good. It's like spa treatment. Jada, what are they asking me to find? How would I get the A by itself? Divide by M all. Good. So you're telling me A is going to be M2G divided by M1 plus M2 M all? Yes. Now let's plug in numbers. What was M2? 2.5? Jada, what was G? Yep, and not negative in this unit. In fact, we decided to let down be positive. It made the math way nicer. All divided by 2.5 plus 6, or 6 plus 2.5. This one I won't do in my... Oh, wait a minute. There is a built-in error check. Jada, if we cut the rope right there, what's the maximum the acceleration can possibly be in free fall? 9.8. Is this object in free fall, or is something you're going to get an answer less than 9.8. So if you're looking for a bit of an error check for typos on your calculator, if there's a hanging mass, you better not get bigger than 9.8. If you do, you've messed up, or you've missed a bracket or done something. Here, I'm going to get 2.5 times 9.8 divided by bracket 2.5 plus 6, or 6 plus 2.5. Do y'all get 2.882352 2.88? Good. Cool. Ruby, what's B want me to find? Okay. We're going to do B two ways. We're going to write an equation for mass 1 and for mass 2. Look at mass 1. Which way is mass 1 accelerating? To the... Who's winning? Who's losing? It's a trick question. In fact, tension equals M1A. Or, I could go look at mass 2. Who's winning? Who's losing? Equals M2A, because I'm just writing an equation. How would I get the T by itself here? I would swappy dance. So I would have M2G minus M2A equals tension. So just for giggles, this half of the room here, use this equation. This half of the room here, use this equation, and we should, if you use your answer button for A, we should get exactly the same answer. So this half of the room, you'll go 6 times answer button. The right half of the room, sorry, I got to reverse everything. You'll go 2.5 times 9.8 minus 2.5 times answer button. I'll do the second one. It's a bit longer. 2.5 times 9.8 minus 2.5 times answer button. No matter what, all of us got 17.2941, 17.3. If we were clever, what was the easiest one to use? Feel free to be clever. But do you have to be clever? Or will you still be okay if you use the other one? Still be okay if you use the other one. I'm not going to do both from now on. From now on, Ella, I'm going to pick the clever one, or the easy one. Turn the page. Ooh. Sarah, back corner, can you read to me the first sentence at the top of the page? We can. That have what? I like this question. I like this. The other ones, gotta be honest, too easy with no friction as far as I'm concerned. Now we're getting to the level I expect you to handle. Wants me to find the acceleration and the chord tension. Now, there's a couple of possibilities. This could be so heavy, friction could be so big, that this is just dangling and at rest. Unlikely, but possible. Certainly, if instead of 3.2 kilograms, if it was 3,000 kilograms, I think a 2.8 kilogram mass dangling off of a cliff is not going to budge a 3,000 kilogram mass. How would I know if I'd guessed wrong? I would have ended up with a negative acceleration, and that would have told me, you got something wonky here. For now, we're going to assume, I think, that it's getting pulled over the cliff. Okay? So, Sarah, this is a job for a free body diagram. What are the forces acting on this 3.2? Get the obvious one. Is there more than one mass in this question? I'm going to call it M1G. What else? Bigger, smaller, or the same size as mg? I don't see any extra vertical forces. Same size. And because I got more than one mass, I'll call it normal force number 1 to go with mass number 1. What else? I see a rope. Yep. Do they want me to include friction this time? Yeah. Which way do you think this mass is sliding? So which way is friction going to be pointing? Yep. Oh. Sarah? Is this mass number 1? I'm even going to call it friction force number 1 to go with mass number 1. Just it works for me, right? Lazy but organized, I think is a phrase I've used. All right. What are the forces acting on second mass? I'll call that M2G. What else? Yes, you were feeling a little right there. Is it sitting on a surface? Is there a normal force? No. Could it be? Yeah, in fact, in Physics 12, I give a question where I tell them it's at rest and they have to figure out what the normal force is. The mass is sitting on a table and nothing's moving. Can handle it. Oh, if it's not moving, A is 0. It actually makes the question look tougher, but it makes it easier because A is 0. But here, no. Who's winning? Which way do you think this is accelerating? So who's winning? Same answer. So which force is winning? Yep. So I'm going to, again, walk along the rope. You'll notice M1G is not along the rope. Winners are anything that ends up pointing down. Losers are anything that ends up pointing up. Okay. Here's my equation then. I got to zoom out a little bit so I can write. I think it's going to be, I'm going to do a little part A right here. It looks like it's going to be winner, then minus tension, plus tension, minus friction force number 1. I think I've reached the end of the rope. So what's that going to equal, Sarah? M. Oh. A. Oh. Nothing like losing a little tension. How would I get the A by itself? All right. A is going to be M2, 2.8. G, 9.8. Ooh. What's our equation for friction? Oh, normal force number 1. All over M1 plus M2. Sarah, do I know mu? The coefficient of friction? Did they tell me? Yep. I don't know the normal force. Oh, but look. I know the force the same size as the normal force. What must be the same magnitude as the normal force? Which one? There's 2 of them in this question. Now we got to be really careful in our vocabulary. M1G. So you know what? I'm going to go like this. I'm going to cross out that FN, and I'm going to put next to it M1G. I think that's enough work for me that shows Diego, I realized I can substitute it with that. Because I think now we can start trying numbers. A is going to be 2.8 times 9.8 minus 0.12 times 3.2 times 9.8 all over 3.2 plus 2.8. Strongly encourage all of you, try typing that in, because actually we're going to get slightly more difficult than this, but this is the level of difficulty you want to be able to handle on your calculator. Oh, bit of a built-in error check. Since M2 is hanging, I know A is less than 9.8 because it's not in free fall. .8 times 9.8 minus 0.12 times 3.2 times 9.8. Close off the top, divided by bracket 3.2 plus 2.8. .9461, and then the threes look like they start to repeat there. Is that right? Yeah. So 3.95 meters per second squared. Ella, what's B you want me to find? Look at the two masses. Which one do you think would be easier to find the tension from because it's less cluttered? I'm going to use M2. Less junk. So, part B. Which way is M2 accelerating? Who's winning? M2G? Who's losing? And stop. I'm only writing an equation for M2, so that must work out to M2A. What's right in front of the T that I don't like? Swappy dance. Plus that there, minus that there. And I'm going to get M2G minus M2A. And Ella, do you mind? I'm going to put the equals T over on that side because that's where we've seen it by itself. I've scrolled down. What was M2? 2.8 times 9.8 minus 2.8 times, I'm going to use my answer button. In fact, I'm going to write ANS to remind myself, use my answer button. 2.8 times 9.8 minus 2.8 times answer button. I get... Did I make a mistake? No? Oh. 16.4? Is that right? Units. It's a tension. It's a force. Newtons. Yeah. Quick, bunny. We can even handle more than 2 mass. We can handle 10. It just makes a way longer equation. Kind of doing some mental debating here. Well, there's 20 minutes left. It's a Friday, though. I gave you a take-home quiz, didn't I? So here's what I'm going to do. I'm going to pause here so that you can work on the take-home quiz. I am going to give you some homework. Okay? Number 1, you can skip number 2. 1 and 2 are basically identical questions, no friction. Then if you look, number 3, ooh, there's friction there. So when you do your free body diagram, you're going to have a friction force number 1. You're going to have a friction force number 2. Oh, and friction is what times what? Everybody, mu times the? But you can handle it. I haven't done one like that, but I think you can handle it. I haven't done the 3 mass one yet, so I'm going to skip number 4. 5 is good. 6 is even better. 7 is a brain challenge. See if you can figure out 7. I put a star next to it. I'm not going to ask you one that tricky. I haven't done a 3 mass one yet, so I'm going to come back to that. Ooh! Number 9, what are they asking me to find? I haven't done one where I made you get the mu by itself, but hey, Diego, you know what you're going to do? Free body diagram. Who's winning? Who's losing? Winner minus loser equals M all A. Actually, it's at rest. What's your acceleration exactly as a number? What's M all times 0? 0. Get the mu by itself when you're done. Okay? So I haven't done one like this on purpose. See if you can figure it out, number 9. See if you can figure out number 10. Number 12, this is actually from an old Physics 12 scholarship exam. See if you can figure it out. That's for bonus. I'm not going to ask you one that tough. Really, your homework is the take-home quiz. Then I think what's going to happen on Monday, I'm going to finish this lesson off. I'll start the next one. Press pause. We'll finish everything off on Tuesday. Then I have some more quizzes and some review. So we're in good shape to finish the unit off completely by the end of next week. Test the week after. This is by far the longest unit and the trickiest one, forces. It's starting to come together, though. I'm sensing even just the last couple of days, people are wrapping their brain around this better and better and better. So well done.